Welcome back to numerical analysis. That beautiful picture you see rotating in front of you is something called the Lorenz attractor. And today, in our final session in numerical methods, I want to talk a little bit about how the stuff we've been doing up to now can lead us down a road to discover really fascinating and interesting behavior like the Lorenz attractor. So today is Tuesday, I believe, April 21st. Yeah, I think so. And welcome back. This lecture is going to be short and I hope interesting and entertaining even. We've spent a lot of time and work developing numerical methods for ordinary differential equations. And I wanted to cap that off with just a little kind of informational video and lecture on where those kind of techniques really contributed to advances in mathematics in the last 50 years, which is really a blink of the eye in terms of mathematical time, right? So this is pretty recent stuff we'll be talking about today that really did come around because we had numerical methods like the ones we've been talking about that enable this kind of complexity and interesting behavior to be brought to light. So let me begin by just thinking for a minute about how we can visualize solutions to an ordinary differential equation or a system of equations. Here I've just sort of shown you, this is a generic 2x2 system of equations. Two equations, two unknown functions x and y. And the way that we've been visualizing solutions mostly up to now is by visualizing the graph of each solution component, x or y, as a function of time. And that's often exactly what you want to do. But there is another way of visualizing the solutions. And that's the so-called solution trajectories, or sometimes it's called the phase plot for the system. And there, you think of, like in the case of a 2x2 system, you think of the solution values x and y as describing points in the Cartesian plane. And of course, x and y are functions of t, and so as time increases, as time goes on, the x-y pair is going to move. And that traces out a solution curve in this case, R2, two-dimensional space. That's called the solution trajectory or the solution orbit. You're really just doing a parametric plot of the pair of solutions, x of t and y of t. So it's a parametric plot like you studied in calculus. So, for example, when we talked about Airy's system, to illustrate Euler's method for systems of equations, we looked at the plots of x and y as a function of time, and that's what you see here. I've solved the system on the time interval from minus 20 to 2, so t goes from minus 20 to 2, and I used some initial conditions that frankly I forgot. But the red curve is the x component of the solution, and the blue curve is the y component of the solution. But you can also visualize that as a parametric plot. And that's what you're seeing here. So now the axes are not t and x, but x and y. And so each point on this curve here represents an xy value at some time, but at some time t, between minus 20 and 2, but notice t doesn't appear in this plot at all. In fact, it's really useful to see these plots as they're made in real time, because you can see the solution being traced out. Let me switch over to MATLAB here if I can. Yeah, let's get rid of that and that. And here's the MATLAB code that built these plots. So there we see the component of the Airy, the component plot for the solutions. And then I'm going to pull up the parametric plot, and you'll see essentially the x and y values trace out that curve here. So as t, you see the point tracing out our curve here, and that's our x of t and y of t varying as t goes from -3 to 20. And so there you see that phase plot being traced out. And so that's a different way of looking at the solutions, and often a very useful way. Here we see, you can see that the x and y values sort of remain bounded, and almost they kind of oscillate for a while. So they produce this kind of almost closed curve here, but then after a while they become unbounded. Both the x and y values go off, it looks like, to negative infinity. And actually, if you look back at the component solutions, that's what's happening right there. From t equals about, say, -2, the solutions start decreasing, it looks like, towards negative infinity. So we see that in the component plot there, and you also see it in a different way in the phase plot. I want to show you a different system. This is called the Lorenz system. It is a 3x3 system. So 3 unknown functions, x, y, and z, and they satisfy this differential equation, or this system of 3 differential equations. Notice that t never appears explicitly on the right-hand side of these systems, and so this is what's called an autonomous system. If the right-hand side of the ODE doesn't depend on t at all, or explicitly, then the system is called autonomous. This is a very famous system. It was discovered by Edward Lorenz, a meteorologist actually, died in 2008. He brought this system forward in about 1963, it was. And this was one of the very first papers that brought forth the idea of deterministic chaos. That is, a deterministic system that behaves very unpredictably. So this is kind of a canonical example in dynamical systems and chaos theory. We can solve the system using the techniques we generated in class, and this is actually what you're seeing here. This is the component plots. So x is in red, which is kind of down here, y is in blue, and z is in green. So there's 3 components now, so there's 3 graphs on this thing. And I used an adaptive Euler's method to compute this solution. It was order 4, so it was pretty accurate. And I used a local error tolerance. I think it was 10 to the -9th, so I tried to get it pretty accurate. So that's the component plot. That already looks interesting enough because you see all kinds of interesting behavior. The z component seems to oscillate pretty steadily, but there's no real, it's not exactly periodic. The x and y components seem quite a bit correlated, and they tend to have 2 regions. They tend to stay in 2 different regions. They'll stay up here for a while, if you can see where my mouse is pointing, and then a bit later they'll come down and be in this region, and they oscillate between those 2 regions. So that already looks interesting, but where it really gets interesting is when you look at the phase plot. And here you're seeing a phase plot for a certain piece of the trajectory that I've computed. And again, it's good to see these things kind of in real time. So let me switch to MATLAB again. See if I can get out of here and go to my Lorenz system. There's the component plots that you just saw. And here you'll see the phase plot as it gets traced out right here. Now, since this is a 3x3 system, this is in 3 space. So this is actually a 3-dimensional picture. You can rotate, and sometimes rotating it does give you a better idea. You can see that solution kind of oscillating between 2 lobes, one here on the left, right around here, and then another one on the right. And the shape of that region is pretty complex. You can rotate it and begin to get an idea of the shape. In fact, in my next plot, I'm just going to do, it's essentially the plot I started the video with. I'm going to just automatically rotate this guy very slowly so we can try to get an idea of what that uh, solution trajectory looks like. So let's start it rotating. Question for you. Is it rotating clockwise or counterclockwise? If you don't pay careful attention, sometimes it seems like it can reverse, but it's not actually. There we're starting to see that shape of the trajectory, and notice this is the trajectory traced out by a single solution curve. So the solution is really pretty complex. This is called the butterfly attractor for the Lorenz equation because from certain perspectives, and I think one is coming up here pretty soon, begins to look a little bit like a butterfly. And Lorenz, the physicist, the atmospheric scientist, was the one who sort of coined the phrase, what is it? A butterfly flapping its wings in Monaco might cause hurricanes the next month in some other part of the world, China. And that's because of the characteristics of the solutions of this system, which have been studied in great depth over the last 50 years. And I'll talk a little bit more about that as we go on. But here, I think at least you can already see the incredible complexity of the solution of just this 3x3 autonomous system. Not much more complicated in a real way than the equations we've been studying up to now, and yet very complicated dynamics, by which I mean sort of the way the solution traces out that curve in 3 space. So that's the Lorenz system. There's another system that's pretty famous as well called the Rossler system. Rossler was a German kind of jack of all trades. Actually, he's still alive. He's clearly a brilliant person, done a lot of work in a lot of different fields. Also has a reputation as a bit of a gadfly, shall we say, to put it politely. He was one of a group of folks who brought suit against the Large Hadron Collider. He was very concerned that if that experiment went forward, it would produce many black holes that would coalesce and then essentially swallow up the Earth and the solar system in a massive black hole. Fortunately, I guess that didn't happen. The experiment went forward, and we're still here. But anyway, Rossler proposed this system of differential equations around the early 70s. I think it was 72 or something like that. He was aware of Lorenz's work, and he basically asked himself, what is the simplest set of equations that I can come up with that will have dynamics that are similarly complex like we see in the Lorenz equation? And so here you see it. It's another 3x3 system. The interesting thing is the first 2 equations in the system are completely linear combinations of x, y, and z. Only the z component has a nonlinear aspect to it. That's 2 plus z times the quantity x minus 4. So that z times x term makes this system nonlinear, but about as weakly nonlinear as you can be, only a single quadratic nonlinearity. Here's the component plots for the solution of Rossler's system. Again, computed with an Euler method, order 4, adaptive step size. And again, you see some hints of complexity here, which I don't necessarily need to describe. You see it even more strikingly in the phase plot. This is a phase plot for the solution of the Rossler system. Again, a 3-dimensional plot, since it's a 3x3 system. And that pattern is a strange attractor, which is an actual term we'll discuss in a second for the ODE system. Again, let me show you how this works in real time. Pull up the Rossler system in MATLAB here and run it real quick. There we're seeing the component plots. Here's the a single solution being traced out in real time for you as it's computed by MATLAB. So you can see that shape being built up by the system. And notice again that same kind of behavior that we saw in the Lorenz system. That is, the solution isn't just creating a simple closed curve or anything like that. It seems to be tracing out some kind of solid that the solution is sort of traveling on. It looks like that's called a manifold, and again, that's been the study of many mathematicians over the last 50 years or so. Let's take a look at that in 3 space as well and rotate it just so you can get a better idea. There we go. So this is the Rossler attractor. You can see it has this kind of this big mouth-like aspect to it here. And then it's got kind of a flat area down here. It's not really visible here, but it's this area right here. It looks almost like an LP playing. So again, a highly complex solution trajectory for what's, after all, a pretty simple ODE system. The Rossler system, again, almost a linear system, not quite. So just to give you some sort of buzzwords and things that you might think of if you come across this material again, what we're seeing in these cases for the Lorenz system and for the Rossler system are what are called invariant sets for the ODE. Let me take a 3x3 scenario as our setting here. So suppose we got a 3x3 system of ODEs. So the solution trajectory, the XYZ curve that's traced out, will live in 3 space, R3. So a set sigma, a subset of sigma, a subset of R3, let's call it sigma, is said to be invariant for the system if whenever a solution is a member of the set sigma. So this saying, at some time t1, we find that the solution trajectory x of t1, y of t1, z of t1 is a member of this set sigma. If that always implies that for all later times the trajectory remains in sigma, we say that sigma is a invariant set for the system. So an invariant set would mean that, if you imagine the system, the solution of the system tracing out a curve in R3, if there's some subset of R3, and once the system enters that subset, it never leaves, that subset is called an invariant set for the system. Now, and being an invariant set is one thing, but an invariant set may also be what we call an attractor. An invariant set is an attractor if, in addition to being an invariant set, they're sort of like a basin of attraction. There's this open set U containing sigma, such that once the solution enters U, then there must be some later time when it also enters sigma. So there's this region sort of around the invariant set, and even though that's not part of the invariant set, if you start the solution trajectory in this region U, then the solution will be attracted to the invariant set, and then once it's an invariant set, of course, once the solution enters an invariant set, it stays in that invariant set for all time. So the Lorenz attractor and the Rossler attractor are both attracting invariant sets in this sense as well. And then finally, we have the concept of a strange attractor. So a set is called a strange attractor if A, it's an attracting invariant set, and B, the set has what we call a fractal structure. And so I won't get into the details of what fractal structure means, but it means what you think it means. If you've seen those pictures all over the place of fractals, you have this kind of self-similar structure that can be defined rigorously. And so that's what we require for a strange attractor, is some sort of fractal structure. And it turns out it was proven in 2002 by Tucker, a mathematician, that the Lorenz system indeed has a strange attractor. And that is actually also true for the Rossler system. Mathematicians didn't greet this theorem as big news. It was an important result because it was on a list of problems by an eminent mathematician named Stephen Smale, who thought this was an important problem to solve, and so it was solved. That's good. But mathematicians had suspected for quite a while that the Lorentz system did indeed have a strange attractor, and it was finally proven in 2002. So I just wanted to show you these last bits of info to show you that, you know, the techniques that we've developed have gotten us to the cusp where we can see the kinds of problems that have driven some cutting edge math research over the last 50 years or so. And really, the kind of behavior that you're seeing in the Lorenz system and the Rossler system is so complex that we wouldn't have been able to even know that it was there had we not had accurate numerical methods for computing these solutions. Because, as I mentioned before, these equations, they have solutions, but they're certainly not elementary functions that you can write down in any finite way using the normal functions of calculus, like, you know, e to the x, sine of x, and so on. So, we've come a long way this semester. I want to thank each and every one of you for sticking it out, especially in these most trying of circumstances. I appreciate the work you're doing, and I know some of you are working hard to finish homework assignments. I'm sure you'll be glad to know that I'm not going to put out any new homework assignments. There's plenty, I think, we've done already, and I know many of you are trying to get caught up, so I want to give you the rest of the week to do that. Remember that I'm here if you need consultation, want to ask me questions, whether by email, FaceTime, or whatever. I certainly have enjoyed the course. It was great meeting you, if only for half a semester. Feel a little bit cheated about that. I miss our classroom times, which were always, I thought, full of good humor and good feeling and some good mathematics too. So I'll look back on that fondly. I wish you guys the best. I'll be getting in touch with you, each and every one of you, over the next couple of days, letting you know your current exact grade and asking you whether you want to take a final or not. In the meantime, y'all stay healthy, stay well. I hope you can stay in touch. For seniors, congratulations on your last semester at Hampden-Sydney, and I wish you the best. For everyone else, I look forward to seeing you again around campus when things get back to normal, which hopefully will be soon. Y'all take care and have a good one.